So based off of what I saw from our exam 2, our redox reactions is a bit weak. So we're going to go through some of the basics of our redox again first before we start making it more difficult by looking at one method for balancing redox and why it might be necessary to look at it. So first and foremost, it is important that we remember Leo says Gur. Loss of electrons is oxidation. Oxidation. And Gur, gain of electrons, is reduction. Okay? So we would have to have that information at hand. The next part that is important to do is kind of a sequencing. So if you got asked at any level, you'd be able to answer at any level. If something was oxidized, it was, a reducing agent. So if you can keep these things tied, then if we asked for an oxidizing agent, you would know that needs to be reduced, which means it needs to gain electrons. To determine all of that, we have to first be able to figure out our oxidation states. So our our oxidation state or our oxidation number. Our oxidation states and numbers are things that have to be calculated. Okay, that calculation involves a couple things. Number one, you need to know that oxygen is always a -2. Okay, at least as far as we're concerned. You should know the ionic charges, so that if you see an ionic compound, you can split it into the ionic charges. And then the final formal thing is the big charge, or the big formula for calculating all of our oxidation states. Okay, the number of an atom, so how many times it shows up in a formula, times the charge on that atom, plus the number of the next atom, times the charge on that atom, etc., 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 all have to sum to equal the overall charge for your molecule. The overall charge is always written in the upper right-hand corner. There's never an exception to that. It's always specified there. Okay, so all you have to do is make sure that you're looking at that point for your overall charge. Okay, then at that stage, it's now just a question of answering questions. So let's take a look at an equation. If I want to decide if this is a reduction and oxidation reaction, the very first thing to do would be to try and determine oxidation states. The easiest thing to do is to determine the oxidation state for the easiest ones. So anything by itself has a trivial oxidation state calculation. How many times does zinc show up in that unit? It shows up once. Times its oxidation state, there's no other elements there, has to equal its overall charge. The overall charge written in the upper right hand corner is 0. I know the oxidation state is 0. Okay, then I can go through and look for zinc to show up on the product side and see if its oxidation state has changed. If its bonding characteristics have changed, it's likely changed. In this case, it's not being shown in bonds, it's just being shown as the ion. I can tell that zinc is a +2. What happened to the oxidation state? We went from a 0 to a +2. To go from a 0 to a +2, we had to lose electrons. If it's loss of electrons, it was oxidized. Okay? And we now know if that was oxidized, the other species had to have been reduced. Okay? If we're just trying to identify if this was an oxidation or reduction reaction, as soon as we found that the oxidation state has changed, it by definition is an oxidation reduction reaction. Okay? Keeping it relatively simple. Okay? So those are the basic pieces behind it. Okay? The next step that comes with this is that we need to be able to balance these equations appropriately. So when we went through and dealt with balancing, so I'm going to erase everything now. When we go through to deal with balancing, we would usually just count our elements. So zinc 1, 1, hydrogen 1, and 2. Well, that didn't balance out, so we have to put a 2 there, and now everything is balanced. So sometimes it's trivial. Sometimes it's not. Okay, and what do we mean by that not? That not means we'd have to be looking at our charge. So if we try and evaluate the charge for a chemical reaction, it should be the same on both sides. It needs to balance out. So if we look at the charge on the left-hand side, zinc has a 0, hydrogen has a +1. The overall charge on the left-hand side is a +1. If we look to the left, it's a +2 and a 0. The overall charge is +2, which means the charge didn't balance. So that's why we would need a method to ensure that we could balance the equation. Okay? If we looked at the past case where we didn't actually look at charge, we said that we needed 2 hydrogens, which means the charge on the left-hand side is actually a +2. So the charge balanced itself without us having to evaluate it by looking at the number of elements. Sometimes it works like that. Sometimes it doesn't. Okay? So if we take a look at this one and we try and evaluate, oh, you monkeys. Okay? We look at this one and we try and evaluate what happened within it. We might go through and say, well, tin on the left, 1, tin on the right, 1, iron on the left, 1, and 1. So it looks like it's balanced. Okay? At least based off of our standard atom balancing. But what happens when we look at charge? The tin is a +2, the iron is a +3. Overall, on the reactant side, we're at a +5 charge. If we look at our product, it's +4 and +2. Overall, our charge is +6. The charge did not balance. Okay, so trying to come up with a way to balance this could be tricky. Okay, sometimes people can see it. There's a variety of ways to go through and do it. Okay, one of the more common ways to go through and do it is to move to a slightly different reaction system, and that is splitting up the reaction into so-called half reactions. Half reactions, because we'll look at the reduction half reaction and the oxidation half reaction. To decide which one is which, we would have to look at our oxidation states and charges, and I'm going to do that real quickly so I can color code nicely, but it's not a requirement to go through. We just split it into the half reaction. So I went through so I could color code. The iron went from a +3 to a +2, which means it gained electrons, which means it was reduced. The tin went from a +2 to a +4. To make that charge change, it had to have lost electrons, so it was oxidation. So we've now split our reaction into these two half reactions. Because they are half reactions, we are allowed to balance the charges on both sides with electrons. This is not something we're typically allowed to do because electrons aren't stable and can't just exist on their own. But because we're only looking at half of the reaction processing, we're not saying it's actually happening on its own. We're just saying that this half needs to happen, which means the electrons are allowed to show up. So how do I use the electrons? Well, I'm going to add the electrons to the reactant or product side and just see. Okay. One way we could do it on placing the electrons is interpreting what was the reaction. In this case, for the red one, our iron, it gained electrons. But let's say we don't have that content. We're just like, I don't know. Leo says Gur. So I'm just going to add electrons. Because for whatever reason, I'm going to decide it's easier to add electrons to the product side. There we go. We add our electrons to the product side. Let's look at our charge all the way down underneath. The charge on the left-hand side is a +3. The charge on the right-hand side would be a +2 and a -1, which means the charge on the left-hand side is a +1. I actually got further from balancing out the charge, which means I placed the electron on the wrong side. So what I'm going to do is erase the electron on the product side and put it on the reactant side. Now I'm going to go through that exact same process and balance out the charges, okay, or look at my charges. The iron was a +3, +2. I also have that electron, which is a -1 charge. Remember, electrons are a -1. The charge on the reactant side is now a +2, going to a +2. That is now balanced. So I've now appropriately place the electrons. This is the half reaction method. Okay, that's the point. So I can then go through and do the same thing for the tin. Okay, so let's take a look And actually, by let's, I'm going to suggest that you take a look. So go ahead and pause the video. That's hitting the space bar. Click the video. Both of those methods should go through and actually pause the video for you. Pause the video and add electrons to the tin reaction or our oxidation reaction until you're balanced. Hopefully you're coming back and you were like, well, because we added electrons to the reactant side, I'm going to add it to the reactant side again. And let's see what happens. +2 charge, -1 charge, and a +4 charge. I would get a +1 became +4. That actually took me further from where I wanted to be because I want those charges to be the same, which means I clearly put the electron on the wrong side. I'm going to add the electron to the other side now. Okay, when I go through and add the electron to the other side, I'm now adding a -1. The charge on the product side is now a +3. Okay, well, dang. It doesn't matter where I place the electron, I'm still not balancing it. You can add more than one electron. Okay, I did get closer to balancing out those charges. +2 is closer to a +3 than +2 to +4. Okay, which means I could add another electron to the product side. If I add another -1, the charge on the product side now becomes +2, and my charges balance out. So by adding 2 electrons, I've now appropriately balanced that second reaction. It's a bit tedious to write it out as this big long thing, so what we can go through and do is simplify that down and use a coefficient in front. That's the point of the coefficients. So for tin +2 to become tin +4, it must lose 2 electrons. Okay, so why pull it into the half reactions? Remember, our whole goal was to balance the initial equation. Okay, so to balance it, what I've done was split it out into those half reactions. If I'm going to balance it, I'm going to have to put them back together. So if we added these 2 equations back with each other, we could end with the new equation. Fe +3 plus tin +2 goes to Fe +2 plus tin +4. And now instead of it being 1 electron on the reactant and 1 electron on the product, I could simplify, subtract an electron from both sides, and I would say +1 electron. If I now looked at the charge in this new equation, +5, +6, plus a -1, the charge would balance out. So this looks good, except I have an electron left over, and electrons must cancel out. Okay, so I have to go back to my half reactions, and I need to think about how I can possibly combine these half reactions so that the electrons produced in the oxidation are canceled by the electrons gained in the reduction. Okay, since the production one has to produce 2, the reduction one must gain 2. So this has to be a 2 in front. Okay, but if I make that a 2, I'm changing the coefficient in the equation, which is okay as long as I change the coefficient all the way through. So I have to multiply everything through by 2. Okay, now what happens is I'd be able to subtract 2 electrons from both sides. When I go through to total up my equation, I would get 2 Fe +3 plus tin +2 goes to 2 Fe +2 plus tin +4. The electrons cancel out on both sides of the equation. If we went through to check irons, there's 2 on the left, 2 on the right. Tins, 1 on the left, 1 on the right. And if we now looked at charge, what happened on the charge? 2 Fe +3s is a +6. The iron is a +2. My charge on the left is a +8. Charge on the right, 2 Fe +2s is a +4. The tin +4 +8, my charge is balanced too, which means my overall equation, properly balanced, is that one shown in purple. And we could put a big old black box around it. And we've now properly balanced our redox reaction. How did we know to go through and do that? We used the half reaction method to see how many electrons. Okay, so this is effectively, this half reaction method allows us to see electrons which now allows us to balance charge easier. Okay. There are other ways to do it. They're usually internalizing some of that calculation and keeping track of it in your head. As we've said in the past, keeping track of things in your head is generally a bad idea, and so I don't recommend it. Okay? And so that would be our half reaction method. I don't know how this video does with pauses. You've probably seen a whole bunch, but I'm going to call attention to it. I'm going to pause real quickly and skip over some slides. And now we get to some balancing practice. So officially, we've looked at the first two. If for whatever reason you didn't take notes, now's your opportunity to go through and balance those two equations. You can set them up as half reactions. That would be the recommendation. And see how it balances out. And then after you've done that, you can go ahead and try the last one down below and see if you can figure out how to do that one, which is a little bit more complicated. But I'm going to pause the video again here, and I'm going to draw all of that work up above. So I'm going to end up erasing everything above it so that you can see all the work of my process for that half reaction process. Pseudo-stepwising through, we've now split it into our individual half reactions. With the copper, it went from a 0 to a +2, which meant it lost electrons. And a loss of electrons is oxidation, and I've been showing oxidation in blue. That means the red one, the remainder of my pieces, need to be red for our reduction. Okay. Notice I didn't include the hydrogen or the water for our copper reaction, because what I'm trying to do is just summarize the big pieces or the big things that changed. Okay, so to balance out the copper, I only need copper. There's no need for hydrogen or oxygen. Okay, for the other reaction, the nitrogen is the one that changed its oxidation state, but notice the oxygen number changed. Because the oxygen number changed, I needed to include water. But then when I include water, water brings in hydrogen, which then means I needed this hydrogen. Okay, and so that's why all of those pieces went in there also. Okay, so with those split out into half reactions, that might help you do the next step, which is balancing out your electrons. And I'm again going to hide everything. Each reaction is now balanced with our electrons. Note we've got charges written in underneath. You may wonder, or may have initially looked at it and said, well, the charge is balanced out. But what you might not have done was properly balance the number of atoms first. Before balancing charge, make sure you try and balance your atoms within an individual half reaction first. Once we've done that, we know we need one electron on the reactant side for the reduction reaction. Okay, we could now go through and say, well, those electrons aren't going to balance out. I'm going to need to change the coefficient. So I'm going to need to put a 2 in front of my electrons on the reduction so that it can properly cancel the 2 electrons in my oxidation. But if I multiply that 1 by a 2, this 2 needs to get multiplied by 2, so it becomes 4, 2, 2, and 2. We could now add the two equations up. The coefficient in front of our H plus is 4, in front of the copper it's 1, in front of the nitrate it's 2, in front of the copper it's 1, in front of the nitrogen dioxide it's 2, in front of the water it's 2. Our electrons would cancel because they're the same on both sides of the equation, and we now have a properly balanced equation using the half reaction method. If that doesn't make sense, don't stress about it. At this point, it's probably more important to understand how to determine oxidation state and number one, how to determine oxidation state, and number two, how to identify reduction and oxidation reactions. If you can't balance, again, don't stress. If you have to move into 151 or more advanced chemistries, you will encounter balancing via half reactions and other methods again, and hopefully you'll be able to pick it up then. With that, we're going to go ahead and end our section on balancing via half reactions.